Microsoft gave it the most reassuring name they could think of: fast startup. 2 words that tell you exactly what to expect. Your computer starts faster, and when you first heard about it, or when you first noticed your machine booting in seconds rather than the minute it used to take, the feature delivered on that promise in a way that felt genuinely impressive. You pressed the power button, Windows loaded almost instantly. You were at your desktop before you had even finished setting down your coffee. It seemed like one of those rare cases where the operating system just worked better, faster, more efficiently than before, with no catch and no compromise. Except there is a catch. There has always been a catch. And for a significant number of users, on a wide range of hardware configurations, fast startup is not just failing to help their system. It is actively creating problems that look like hardware failures, driver corruption, performance degradation, and baffling inconsistencies that appear and disappear without any apparent cause. The reason your computer sometimes feels sluggish despite a restart. The reason certain devices stop working correctly after what should have been a clean boot. The reason Windows updates sometimes behave strangely even after you restarted to apply them. The reason that turning your computer off and back on, the most fundamental troubleshooting step in all of computing, sometimes does not fix the problem the way it should. Fast startup is quietly responsible for more of this than most users ever realize. Let's go through exactly why. Let's start with what fast startup actually does at a technical level, because the name describes the outcome but conceals the mechanism, and the mechanism is where all the problems originate. Fast startup was introduced in Windows 8 and has continued into Windows 10 and Windows 11. It is enabled by default in Windows 11 on most hardware configurations that support it. And what it does, at its core, is change what happens when you click shutdown. In a traditional full shutdown, the kind that existed before fast startup, clicking shutdown caused Windows to close all running applications, log out the user session completely, terminate all system processes, unload all drivers, and power off the hardware entirely. When you pressed the power button the next morning, the system started from a completely clean state. Every driver was loaded fresh. Every system service was initialized from scratch. The kernel, the core of the operating system, was loaded fresh from the installation files. Every component of the system started its session without any state carried over from the previous one. This is what a proper shutdown and cold boot actually means, and it is why restarting a computer has historically been the most reliable way to clear software problems. Because a true restart eliminates all accumulated runtime state and forces everything to reinitialize cleanly. Fast startup changes this process fundamentally. When fast startup is enabled and you click shutdown, Windows does log out the user session. User-level processes are terminated. But the Windows kernel, the core operating system layer that manages hardware, drivers, and fundamental system services, is not terminated in the way a full shutdown would terminate it. Instead, Windows saves the kernel's state to a file on your hard drive called hiberfil. SIS. This is the hibernation file, the same file used when you select hibernate from the power menu. The kernel state, the loaded drivers, the system service states, all of it is captured in a snapshot and written to disk. Then the machine powers off. When you press the power button the next morning, Windows does not boot from scratch. It reads that snapshot from hiberfil. SIS restores the saved kernel state into memory and resumes from where the kernel was when you clicked shutdown. With all the same drivers loaded, all the same system state in place, all the same kernel-level conditions that existed at the end of your previous session. This is why it is faster. Loading a saved kernel state from a compressed file is dramatically faster than initializing the kernel and all its associated drivers from scratch. The boot time improvement is real, substantial, and the direct result of not actually doing a full restart of the system's core. And that last phrase, not actually doing a full restart of the system's core, is the entire source of every problem fast startup creates. Let's talk about driver state specifically, because drivers are where fast startup's failure mode is most consistently documented and most consequential for everyday users. A hardware driver is software that provides the interface between the Windows operating system and a specific piece of hardware. Your graphics card, your network adapter, your USB controller, your storage controller, your audio hardware. Drivers run at the kernel level, meaning they are part of the core system layer that fast startup saves and restores rather than reinitializing fresh on each boot. When a driver runs through a full session, processing hardware interactions, managing interrupts, handling state changes, it accumulates runtime state. In many cases, that state is handled cleanly and terminated properly by a full shutdown. But in some cases, drivers develop what engineers call state drift over the course of a session. Subtle inconsistencies in their internal state that accumulate over time and that a full driver reload on next boot would clear automatically. With fast startup enabled, that state drift is not cleared at shutdown. The The driver state is saved along with the rest of the kernel snapshot and restored on next boot. You are not starting with a fresh driver. You are resuming with the same driver in the same accumulated state it was in when you clicked shutdown. And if that state includes a subtle inconsistency, a memory leak that has not yet become critical, a buffered operation that was not properly flushed, an interrupt flag in an incorrect state, that inconsistency is carried into your next session and may compound further as the new session adds its own state changes on top of the existing ones. This is the mechanism behind a class of problems that users report regularly but rarely connect to fast startup. Hardware that works intermittently, devices that need to be unplugged and replugged to function after boot, network adapters that show as connected but fail to pass traffic until disabled and re-enabled, graphics drivers that produce artifacts or instability that was not present at the start of the previous session, USB devices that are not recognized after what the user believes was a full shutdown and restart. In each of these cases, the device or driver was not actually reset. It was resumed from a saved state, and the inconsistency that caused the problem was preserved across the apparent shutdown boundary rather than being cleared by it. The USB controller behavior deserves specific attention because it is one of the most widely reported and most clearly documented manifestations of fast startup's driver state problem. USB controllers maintain connection state for all connected devices. In a full shutdown, those connections are properly terminated, the controller state is reset, and on next boot, every USB device goes through a proper enumeration process. The handshake sequence, by which the USB controller identifies the device, negotiates its operating parameters, and establishes a clean communication channel. With fast startup, the USB controller state is saved and restored, and many USB devices do not go through a fresh enumeration on the next session. They are simply assumed to be in the same state they were in when the system went down. This assumption fails in a surprising range of circumstances. When the device was connected or disconnected while the system was powered off, when the device's own internal state has reset while power was removed, or when the device's firmware and the driver's restored state have a mismatch, because the device started fresh while the driver did not. USB audio interfaces, external hard drives, drawing tablets, gaming peripherals, and specialized input devices are among the categories most frequently reported as behaving incorrectly after fast startup resumption rather than full cold boot. The fix in almost every one of these cases is identical. Disable fast startup, perform a genuine full shutdown and cold boot, and observe whether the problem recurs. In a large proportion of reported cases, it does not. Let's talk about something that catches a significant number of users completely off guard. The behavior of Windows Update in relation to fast startup. Windows Update often requires a restart to complete the installation of certain updates, particularly driver updates, cumulative updates that modify kernel-level components, and major feature updates. The restart requirement exists specifically because some updates need the kernel to be fully unloaded and reloaded fresh in order to replace files that are in use during an active session. When you see the Restart Now to complete the update prompt and you click it, you are supposed to be getting a full restart, a complete shutdown and cold boot that allows the update installation to complete during the boot process before the old versions of the updated components are loaded. With fast startup enabled, there is a documented discrepancy between what the user believes is happening and what is actually happening. The restart prompted by Windows Update and the restart that occurs when you specifically select Restart rather than Shut Down from the Power menu does perform a full restart, because Microsoft's update infrastructure is designed to trigger a genuine restart rather than a fast startup resume cycle. But users who click Shut Down instead of Restart during the update process, which is a natural mistake to make because shutdown intuitively sounds like the more complete action, may get a fast startup hibernate resume cycle instead of the full shutdown and restart that the update actually requires. This means the update may not complete correctly. The files that needed to be replaced were not replaceable during the resume cycle because the kernel that holds them was never fully unloaded. The system appears to have rebooted. Windows may no longer show the pending update prompt, but the update is not fully installed, and the system is running in an inconsistent state where some components have been partially updated and others have not. This specific scenario, a partially applied update resulting in subtle system instability, security gaps in components that were supposed to be patched, or features not functioning as expected after an update that appeared to apply successfully, is one of the more serious real-world consequences of fast startup and one of the most difficult to diagnose because the visual indicators all suggest the update completed normally. Let's address the dual boot scenario, because for users running both Windows and Linux on the same machine, fast startup is not merely a performance or driver concern. It is a direct data integrity risk that is widely documented and clearly understood in the dual boot community. when Windows 11 with fast startup enabled writes the kernel state snapshot to Hyberfill. sys and powers off any partitions that Windows had mounted, including shared and TFS partitions, are left in a state that Windows considers mounted with cached writes, rather than cleanly unmounted. From Windows' perspective, they will be cleanly remounted when the session resumes from the snapshot. From the perspective of Linux, booting after a Windows fast startup shutdown sees those partitions in an indeterminate mounted state, and will typically either refuse to mount them in read-write mode, showing an error about the volume being in an unsafe state, or mount them in a degraded mode that risks data corruption if any write operations occur before Windows has had the opportunity to properly resume and commit its cached state. This is not a theoretical risk. The Linux community has extensively documented cases of NTFS partition corruption and data loss resulting from Linux writing to partitions that were left in fast startup's interrupted mounted state. For any user running a dual boot configuration, fast startup is a feature that should be disabled unconditionally, with no exceptions, regardless of any performance benefit it might offer. Let's now talk about RAM and memory management, because fast startup interacts with memory in a way that creates a specific class of problem related to how Windows manages physical RAM across sessions. In a normal boot, Windows initializes its memory management from scratch, mapping physical RAM, setting up virtual memory, establishing the page file, and building the structures that track what memory is allocated, what is free, and what has been paged out to disk. In a fast startup resume, these memory management structures are restored from the snapshot along with everything else. If the previous session had accumulated significant memory fragmentation, many small allocations scattered across physical RAM, leaving insufficient contiguous free space for operations that require it, that fragmentation is carried into the new session. On machines with limited RAM, this can mean that a session started via fast startup begins with a more constrained memory environment than a session started via a full cold boot, specifically because the memory management structures inherited from the previous session have not been rebuilt fresh. The practical manifestation is an application that loads more slowly or more memory intensively at the start of a fast startup session than it would have at the start of a cold boot session, a result that is precisely the opposite of what users who see their desktop appear quickly after a fast startup assume about their system's resource availability. The Hyberfill. Sysfile itself is another consideration that many users do not account for when evaluating fast startup. The hibernation file that stores the kernel state snapshot is not a small file. Its size is proportional to the amount of RAM in the system. On a machine with 16 GB of RAM, Hyberfill, sys can occupy several gigabytes of storage. On a machine with 32 GB of RAM, it is proportionally larger. This space is permanently reserved on the system drive as long as fast startup or hibernation is enabled, reducing the available storage for actual data. On machines with smaller SSDs, particularly the 256 GB drives common in budget and mid-range laptops, several gigabytes permanently consumed by Hyberfill. Sys, for the purpose of enabling a faster startup time, is a trade-off that many users would not make deliberately if they were clearly informed about it. There's also a thermal and hardware wear consideration that is less frequently discussed but genuinely relevant for laptop users specifically. In a proper shutdown, hardware components, the SSD, the RAM modules, the CPU, the GPU, go through a clean power down sequence. Thermal management systems complete their shutdown procedures. Fan control is properly terminated. In a fast startup scenario, the power down happens from a more abrupt state, and depending on the specific hardware implementation, the interaction between the saved kernel state's hardware management expectations and the actual hardware state after it has been unpowered and repowered may create subtle inconsistencies in hardware management on resume. Inconsistencies that can affect thermal management behavior, power delivery regulation, and battery charging behavior on laptops in particular. Battery calibration and health monitoring software on laptops often behaves incorrectly with fast startup enabled, specifically because the battery management driver is restored from a saved state rather than reinitializing with a fresh read of the battery's actual state on each boot. Users have reported incorrect battery percentage readings, premature low battery warnings, and battery health monitoring inaccuracies that are directly attributable to the driver resuming from a saved state rather than performing a fresh initialization and reading of the battery's current status. Now let's go through exactly what to do. How to disable fast startup completely, how to verify that your shutdowns are actually performing full shutdowns, and what a properly configured power management setup looks like for a Windows 11 machine. The first step is locating the fast startup setting, because it is not in the obvious location. It is not in the main power settings in the Settings app. It is in the Legacy Control Panel Power Options. Open Control Panel, type it in the Start menu search, then navigate to Hardware and Sound, then Power Options. Then on the left sidebar, choose what the power buttons do. On this page, you will see a section called Shutdown Settings with a checkbox labeled Turn on Fast Startup, recommended. The word recommended in parentheses is Microsoft's framing, not a universal technical recommendation. Uncheck this box and click Save Changes. Fast Startup is now disabled. There's one important detail about this step that trips up many users. The checkbox for Fast Startup may be grayed out, visually present but not interactable. This happens when the Hibernate feature is disabled on the system because Fast Startup depends on the Hyberfil, sys hibernation file infrastructure. If Hibernate is disabled, Fast Startup is automatically disabled as well, and the checkbox is grayed out to reflect that it is not applicable. If this is what you see, Fast Startup is already not functioning on your machine and no further action is needed for this specific setting. The second step is verifying that your shutdowns are actually full shutdowns after disabling Fast Startup. The most reliable way to verify this is through the Windows Event Log, which records boot events with specific codes that distinguish between a Fast Startup resume and a true cold boot. Open Event Viewer, search for it in the Start menu, navigate to Windows Logs, then System, and look for Event ID 1 from the kernel power source, which is recorded at System Startup. Cross-reference with Event ID 42 from the kernel power source. This event is recorded when the system enters hibernation or hybrid sleep, which Fast Startup uses. If you see Event ID 42 recorded at shutdown but no longer see Event ID 1 consistent with resume from hibernation behavior, after disabling Fast Startup, the change has taken effect. The third step, for users who want a command line approach or want to ensure Hibernate itself is fully disabled, which also guarantees Fast Startup cannot function, is to open an elevated command prompt or PowerShell window and run the command powercfg h off. This command disables hibernation entirely, deletes the Hyberfil sys file, and reclaims the storage space it was occupying. With hibernation disabled, Fast Startup has no mechanism to function, making this a more comprehensive solution than simply unchecking the checkbox in Control Panel. The trade-off is that the Hibernate option disappears from your power menu, which may matter for users who deliberately use Hibernate for its intended purpose of preserving session state during extended periods of inactivity. The fourth step is understanding the correct restart procedure for applying Windows updates and for general troubleshooting, now that you have disabled Fast Startup. When you need to apply an update that requires a restart, use the Restart option, not Shutdown, from the power menu. Restart performs a full shutdown and cold boot regardless of Fast Startup settings. And now that Fast Startup is disabled, Shutdown also performs a full shutdown. But building the habit of using Restart for update application is correct practice regardless. The fifth step addresses the storage space reclamation aspect. After running powercfg h off, or after disabling Fast Startup through Control Panel, run the disk cleanup utility on your system drive and specifically check whether Hyberfil, sys-related items appear in the cleanup list. On systems where the file has been removed by the powercfg command, the space will already have been reclaimed. On systems where Fast Startup was disabled through the checkbox but Hibernate was not disabled, the Hyberfil SIS file may still exist and may be accessible for cleanup through the Disk Cleanup Tool's Hibernate File Cleaner option. The sixth step is checking your sleep settings to ensure that the power management configuration is coherent now that Fast Startup is disabled. Open Settings, then System, then Power, and review the sleep and display timeout settings. With Fast Startup disabled, sleep and Hibernate become the primary mechanisms for preserving power during inactivity periods rather than the shutdown cycle. Configuring appropriate sleep timeouts for your usage pattern, shorter on a laptop where battery conservation matters, longer or disabled on a desktop where immediate wake from sleep without hibernation overhead is preferred, ensures that disabling Fast Startup does not leave your machine without appropriate power management behavior during idle periods. The seventh step is particularly relevant for users who have been experiencing the driver-related issues we described. USB devices not working correctly, network adapters behaving inconsistently, graphics issues persisting across sessions. After disabling Fast Startup and performing a genuine cold boot, these issues should be reevaluated fresh. In many cases, a cold boot following Fast Startup disablement resolves the issue entirely, confirming that the Fast Startup resume cycle was carrying problematic driver state across sessions. In cases where the issue persists after a genuine cold boot, the underlying cause is something other than Fast Startup, a driver update, a hardware fault, or a configuration issue, and should be investigated accordingly rather than being assumed to be a Fast Startup artifact. The eighth step is for dual boot users specifically, and it cannot be overstated in its importance. If you run Linux alongside Windows 11 on the same machine, disabling Fast Startup is not optional and not a performance trade-off. It is a data integrity requirement. After disabling fast startup, verify that any shared NTFS partitions are being mounted in read-write mode by Linux without error messages about unsafe or dirty volume states. If such errors were previously occurring, their disappearance after fast startup disablement confirms the source of the problem and the effectiveness of the fix. Let's close with the broader principle that fast startup illustrates about how Windows default configuration priorities interact with actual hardware reality. Fast startup was designed to solve a specific real user complaint: slow boot times. It solved that complaint in a way that is technically clever and genuinely effective at the specific goal of making the boot sequence shorter. But it solved it by fundamentally changing what shutdown means, without clearly communicating that change to users, and without adjusting the user's mental model of what a shutdown and restart actually does to the system. Users who click shutdown and believe they have performed a full system reset are wrong, and the consequences of being wrong range from minor inconveniences to data corruption to persistent hardware management problems that are genuinely difficult to diagnose when you do not know the underlying mechanism. The name fast startup tells you about the speed. It does not tell you that it works by never fully shutting down. It does not tell you that your drivers are resuming from a cached state. It does not tell you that your USB devices may not reinitialize cleanly. It does not tell you that your Windows updates may not apply correctly if you use shutdown instead of restart. It does not tell you that your dual boot Linux installation may corrupt your NTFS data. It does not tell you that it permanently occupies several gigabytes of your storage for a hibernation file. All of these things are true. None of them are in the feature's name, and all of them together explain why a feature that sounds like a pure, cost-free improvement is, for a significant number of users and use cases, something that should never have been their default. Now you know what it actually is. You know where to find it. You know how to turn it off. And you know why the few seconds it saves at boot have been costing you far more. In driver consistency and update reliability, in storage space, and in the simple trustworthiness of the most basic troubleshooting action in computing than you ever got back. Turn it off. Do a real shutdown. Boot from scratch. And notice how much better a machine that actually starts clean behaves compared to one that has been resuming from the same accumulated state for months.